Hello guys, today I will be tackling these network essentials from the TryHackMe Cybersecurity 101 path. Yeah, this is the next module that I have here on the path. I've already completed all of them. Networking concepts is the one I did yesterday. Today we're going to tackle the networking essentials. Without further ado, let's get right down to it. Okay. Have you ever wondered how your computer can dynamically configure its network settings when you turn it on or connect it to a new network? Have you ever wanted to know how many devices and countries your packets pass through before reaching their destination? Are you curious how all your home devices can access the internet even though your internet service provider gives you a single IP address? If you want to know the answers to these questions, among others, then this room is for you. This room is the second room in the series 4 rooms about computer networking. Learning prerequisites. To benefit from this room, we recommend that you know the following: ISO OSI model and layers, TCP/IP model and layers, Ethernet, IP, and TCP protocols. In other words, starting this room after networking concepts is the recommended approach. Yeah. Learning objectives. The objective of this room is to teach you about various standard protocols and technologies that glue things together. Dynamic host configuration protocol, address resolution protocol, network address translation, internet control message protocol, ping, traceroute. Get your notepad ready and let's begin. Okay, DHCP, give me my network settings. You went to your favorite coffee shop, grab your favorite hot drink, and open your laptop. Your laptop connected to the shop's Wi-Fi and automatically configured the network. So you could now work on a new TryHackMe room. You didn't type a single IP address, yet your device is all set up. Let's see how this happened. Whenever we want to access a network, at the very least, we need to configure the following: IP address along with subnet mask, router or gateway, DNS server. Whenever we connect our device to a new network, the above configurations must be set according to the new network. Manually configuring these settings is a good option, especially for servers. Servers are not expected to switch networks. You don't carry your domain controller and connect it to the coffee shop Wi-Fi. Moreover, other devices need to connect to the servers and expect to find them at specific IP addresses. Having an automated way to configure connected devices has many advantages. First, it will save us from manually configuring the network. This is extremely important, especially for mobile devices. Secondly, it saves us from address conflicts. When two devices are configured with the same IP address, an IP address conflict would prevent the involved hosts from using the network resources. This applies to local resources and the internet. The solution lies in using Dynamic Host Configuration Protocol, the DHCP. This is an application level protocol that relies on UDP. The server listens on UDP port 67 and the client sends from UDP port 68. Your smartphone and laptop are configured to use DHCP by default. Discover, offer, request, acknowledge. Okay. DHCP follows 4 steps. Discover, yeah, the one that we just mentioned, DORA. DHCP discover, the client broadcasts a DHCP discover message seeking the local DHCP server if one exists. DHCP offer, the server responds with a DHCP offer message with an IP address available for the client to accept. DHCP request, the client responds with a DHCP request message to indicate that it has accepted the offered IP. DHCP acknowledge, the server responds with a DHCP pack message to confirm that the offered IP address is now assigned to this client. Okay? The following packet captured shows the 4 steps explained above. In this example, the client gets the address 192.168.66.133. Okay, T-shark minus R, DHCP dot pcap minus N. Okay, so in the DHCP packet exchange, we can notice the following. The client starts without any IP network configuration. It only has a MAC address. In the first and third packets, DHCP discover and DHCP request. Yeah. The client searching for a DHCP server still has no IP network configuration and has not yet used the DHCP server offered IP address. Therefore, it sends packets from the IP address 0.0.0, right, to the broadcast IP address 255.255.255, blah, blah, blah. As for the link layer, in the first and third packets, the client sends to the broadcast MAC address, this address not shown in the output above. The DHCP server offers an available IP address along with the network configuration in the DHCP offer. It uses the client's destination MAC address. It used the proposed IP address in this example system. Yeah, okay. At the end of the DHCP process, our device would have received all the configuration needed to access the network or even the internet. In particular, we expect that the DHCP server has provided us with the following: the least IP address to access network resources, the gateway to route our packets outside the local network, a DNS server to resolve domain names. More on this later. Okay, how many steps does the DHCP use to provide network configuration? 1, 2, 3, 4? Yeah. What is the destination IP address that a client uses when it sends a DHCP discover packet? 255, 255, 255, 255. What is the source IP address a client uses when trying to get IP network configuration over DHCP? 0.0.0.0. Right? That was clear. Okay. Next one is ARP, bridging layer 3 addressing to layer 2 addressing. Okay? We have stated in the networking concepts room that as two hosts communicate over a network, an IP packet is encapsulated within data link frame as it travels over layer 2. Remember that the two common data link layers we use are Ethernet and Wi-Fi. Whenever one host needs to communicate with another host on the same Ethernet or Wi-Fi, it must send the IP packet within a data link layer frame. Although it knows the IP address of the target host, it needs to look up the target's MAC address so the proper data link header can be created. As you remember, a MAC address is a 48-bit number typically represented in hexadecimal notation. For example, this one and this one are two MAC addresses on my network. Okay, however, the devices on the same Ethernet network do not need to know each other's MAC addresses all the time. They only need to know each other's MAC addresses while communicating. Everything resolves around IP addresses. Consider this scenario. You connect your device to a network, and if the network has a DHCP server, your device is automatically configured to use a specific gateway, router, and DNS server. Consequently, your device knows the IP address on the DNS server to resolve any domain name. Moreover, it knows the IP address of the router when it needs to send packets over the internet. In all these scenarios, no MAC addresses are revealed. However, two devices on the same Ethernet cannot communicate without knowing each other's MAC addresses. As a reminder, in the screenshot below, we see an IP packet within an Ethernet frame. The Ethernet frame header contains destination MAC address, source MAC address, type in this case, IPv4 in this case. Okay. So this is the destination MAC address, the source, destination. This is the source, right? Yeah, for 4. Yeah, okay. And then the type of IPv4. Address resolution protocol makes it possible to find the MAC addresses of another device on the Ethernet. Yeah. In the example below, a host with the IP address of this one wants to communicate with another system with the IP address of this one. It sends an ARP request asking the host with the IP address of this one to respond. The ARP request is sent from the MAC address of the requester to the broadcast MAC address, this one. As shown in the first packet, the ARP reply arrived shortly afterwards, and the host with the IP address of the one we were looking for responded with its MAC address. From this point, the two hosts can exchange data link layer frames. Okay. If we use TCP dump, the packets will be displayed differently. It uses the terms ARP request and ARP reply. For your information, the output is shown in the terminal below. Okay. An ARP request or ARP reply is not encapsulated within a UDP or even IP packet. It is encapsulated directly within an Ethernet frame. The following ARP reply shows this. Sender IP address and the target MAC address and the target IP address. Okay. ARP is considered layer 2 because it deals with MAC addresses. Others would argue that it is part of layer 3 because it supports IP operations. What is essential to know is that ARP allows the translation from layer 3 addressing to layer 2 addressing. What is the destination MAC address used in the ARP request? Destination MAC address, destination MAC address, destination MAC address. Well, it would be this one, C5E F8 02 21 87. Am I right? No, I'm not. What is the destination MAC address used in an? What is the destination MAC address? Oh, in an ARP request? Well, I would assume destination MAC address in an ARP request. Would it be this one? DHCP. We'll see, we'll see. CZ5E. CZ5E. F802. 0202 or 02. 21E7. E7, right? Is that A? Yeah, it was A. Uh-oh. I'm doing something wrong. Oh, I think it's this one, right? FF. Yeah. In the example above, what is the MAC address of 192.168.661? The MAC address is 44 BF 65 B8 FE 66E. Yeah. ICMP troubleshooting networks. Internet Control Message Protocol. Okay, it's mainly used for network diagnostics and error reporting. Two popular commands rely on ICMP, and they are instrumental in network troubleshooting and network security. The commands are ping and traceroute. This command uses ICMP to test connectivity to a target system and measures the round trip time. In other words, it can be used to learn that the target is alive and that its reply can reach our system. Traceroute, this command is called traceroute on Linux and Unix-like systems, and traceRT on MS Windows systems. It uses ICMP to discover the route from your host to the target. You may have never played ping pong, table tennis before, however, thanks to ICMP, you will now play with the computer. Ping command sends an ICMP echo request, ICMP type 8. The screenshot below shows the ICMP message within an IP packet. Okay. The computer on the receiving end responds with an ICMP echo reply, type 0. Yeah. Many things might prevent us from getting a reply, in addition to the possibility of the target system being offline or shut down. A firewall along the path might block the necessary packets for ping to work. In the example below, we used -C4 to tell the ping command to stop for sending 4 packets. Okay, the output shows no packet loss. Moreover, 0% packet loss. It calculates the minimum, average, maximum, and standard deviation on the round trip time, RTT. Traceroute. How can we make every router between our system and the target system reveal itself? The Internet Protocol has a field called time to live that indicates the maximum number of routers a packet can travel through before it is dropped. The router decrements the packet's TTL by 1 before it sends it across. Okay. When the TTL reaches 0, the router drops the packet and sends an ICMP time exceeded message. The ICMP type 11. In this context, time is measured in the number of routers, not seconds. Okay. The terminal output below shows the result of running traceroute to discover the routes between our system and example.com. Some routers don't respond. In other words, they drop the packet without sending any ICMP message. Routers that belong to our ISP might respond, revealing their IP address. Moreover, some routers respond and show their public IP address, and this will let us look up their domain name and discover their geographic location. Finally, there is always a possibility that an ICMP time exceeded message gets blocked and never reaches us. Okay. Using the example images above, how many bytes were sent in the echo pin request? In the echo pin request, this is the echo pin request. How many bytes? 40. It says 40. Which IP header field does the traceroute command require to become 0? Which IP header field? Well, TTL routing. Okay. Consider the network diagram shown below. It only has three networks. However, network 2, network 1, network 3. Okay. On the internet, on the routers, they interact between them too. Okay. However, how can the internet figure out how to deliver a packet from network 1 to network 2 or network 3? Although this is an overly simplified diagram, we need some algorithm to figure out how to connect network 1 to network 2 and network 3 and vice versa. Let's consider a more detailed diagram. The internet would be millions of routers and billions of devices. The network below is a tiny subnet of the internet. The mobile user can reach the web server. However, for this to happen, each router across the path needs to send the packets via the appropriate link. Obviously, there's more than one path. Route connecting the mobile user and the web server. We need a routing algorithm for the router to figure out which link to use. Yeah. The routing algorithms are beyond the scope of this room. However, we will briefly describe a few routing protocols so that you become familiar with their names. OSPF, Open Shortest Path First, is a routing protocol that allows routers to share information about the network topology and calculate the most efficient paths for data transmission. It does this by having routers exchange updates about the state of their connected links and networks. This way, each router has a complete map of the network and can determine the best routes to reach any destination. EIGRP, Enhanced Interior Gateway Routing Protocol, is a Cisco proprietary routing protocol that combines aspects of different routing algorithms. It allows routers to share information about the networks they can reach and the cost, like bandwidth or delay, associated with those routes. Routers then use this information to choose the most efficient paths for data transmission. BGP, Border Gateway Protocol, is the primary routing protocol used on the internet. It allows different networks, like those of internet service providers, to exchange routing information and establish paths for data to travel between these networks. BGP helps ensure data can be routed efficiently across the internet, even when traversing multiple networks. And RIP, Routing Information Protocol, is a simple routing protocol often used in small networks. Routers running RIP share information about the network they can reach and the number of hops or routers required to get there. As a result, each router builds a routing table based on this information, choosing the routes with the fewest hops to reach each destination. Which router protocol discussed in this task is a Cisco proprietary protocol? Well done. EIGRP. NAT. Okay, as discussed in the networking concepts room, we calculated that IPv4 can support a maximum of 4 billion devices. With the increase in the number of devices connected to the internet, from computers and smartphones to security cameras and washing machines, it was clear that the IPv4 address space would be depleted quickly. One solution to address depletion is network and address translation. The idea behind NAT lies in using one public IP address to provide internet access to many private IP addresses. In other words, if you're connecting a company with 20 computers, you can provide internet access to all 20 computers by using a single public IP address instead of 20 public IP addresses. Note, technically speaking, the number of IP addresses is always expressed as a power of 2. To be technically accurate, with NAT, you reserve 2 public IP addresses instead of 32. Consequently, you would have saved 30 public IP addresses. Unlike routing, which is the natural way to route packets to the destination host, routers that support NAT must find a way to track ongoing connections. Consequently, NAT supporting routers maintain a table translating network addresses between internal and external networks. Generally, the internal network would use a private IP address range, while the external network would use a public IP address. In the diagram below, multiple devices access the internet via a router that supports NAT. The router maintains a table that maps the internal IP addresses and port number with the external IP address and port number. For instance, the laptop might establish a connection with some web server. From the laptop perspective, the connection is initiated from its IP address, okay, from TCP source port number 15401. However, the web server will see the same connection as being established from 212.345 and TCP port number, okay, 19273 as shown in the translation table below. The router does this address transition seamlessly. Mm-hmm. In the network diagram above, what is the public IP that the phone will appear to use when accessing the internet? The phone will appear to use. What is the public IP? Oh, well, 212.3.4.5. That's the one, right? That they will all be using. Assuming that the router has infinite processing power, approximately speaking, how many thousand simultaneous TCP connections can we maintain? How many thousands can it maintain? Where's the hint? We are limited by the number of TCP port numbers. Oh yeah, how many TCP port numbers do we have? $65. Yeah. Okay, closing notes. This room introduces various protocols that we constantly use directly or indirectly. We have covered ICMP, DHCP, ARP, NAT, and routing. Although we use the internet daily without coming across most of these rooms acronyms, these protocols are the foundation for a functional network. Click on View the Site. Okay, View the Site. To access the related site, please follow the instructions on the site to obtain the flag. Which protocol do we need? Okay, as we have learned in this room, different protocols and techniques are used to solve various problems. In this exercise, we will help this computer get the information it needs. For each question, we need to select the protocol that best helps answer the question. Okay, start. I want to find another host's hardware MAC address on the network. Which protocol lets me get this information? Is it DHCP? Wrong choice. It's an ARP. Yeah, good, correct answer. Okay. We need to give 25 devices internet access. However, we only have one public IP address. What can we use to allow multiple private IP addresses to use a single public IP address? That is the DHCP. What? Okay, again, I'm curious about tracing the route of packets as they travel to their destination server. What protocol will let me discover the path? Well, the path, that would be routing. Where is routing? Which protocol are we talking about here? I'm curious about tracing the route of packets as they travel to their destination server. What protocol will let me discover the path? Probably ICMP. Correct answer, okay. I want to confirm that I can exchange packets with another host as if I am playing ping pong. Which protocol supports this? ICMP. Yeah. I want to obtain an IP address to use and communicate with the other hosts on the network. What should I use? It's not NAT, it's probably ARP. No. DHCP, give me my network settings. Yeah, that was the one. I want to find out the DNS server and default route on a network automatically. Which protocol should I use? On default route, DHCP. Congratulations. Okay. Got it. We did it. It's time to join networking protocols. Okay. We can minimize this. It is time to join networking core protocols. Yeah. Let's submit this. Then complete. That's it, guys. Let's see, what do we have? 7 days trick phrase. I already have that. Okay, on to the next. On to the next. Thank you for staying with me, guys. This was fun. Good reminders.